in order to make your dream better, okay, I will show you that you should not worry about the equation. Now let's take a look at what we can do with that equation, right? Okay. Usually you do not want to know, okay, this is the equation, so what we can do with that. Okay, so this is your equation. Conservation of mass, conservation of momentum. Simple, right? After those derivation, this is the end product. Actually, you will see this again and again and again. Even in your final exam, maybe this one is in the appendix. Maybe. If I'm in a good mood, maybe this one is the appendix. If not, then you need to remember it. Okay, so as I said to you, at the moment, there is no exact solution of Navier Stokes. It is very complex. It's highly non-linear and you cannot solve it at the moment. But there is always a light in the darkness. You can use it, you can solve it exactly for a very specific cases. And so far only 4 cases can be solved with it. Okay, we will go for the first one is when you have a flow scenario number 1, which is steady and compressible flow between fixed plate. This is the easiest one. Second, when the plate, one of it is moving. It can be the top plate moving or the bottom plate moving, but still parallel plate. Or maybe you have it inclined. Then the flow is due to the gravity. The inclination angle can be as low as 10 degrees or as high as 90 degrees, which means it becomes a vertical plate, not horizontal anymore. It is a vertical plate. Or you can have it in a circular tube. For your information, this one is enrichment, which means it will not be there in your quiz, in your assignment, in your exam. This one is just there for you if you want to learn more. Right? If you do not want, it will not affect your exam. Okay? But if you want to look at it, it is there, available for you. Right. So now, let's take a look at the flow scenario number 1. Act 1, Scene 1. Scene 1, Act 1. You have incompressible flow flowing between 2 infinite parallel. Okay? Due to the slip condition, you remember what is slip condition? When a fluid flow and make a contact with the surface, right? Due to the no slip condition, the fluid will have the velocity similar to the velocity of the surface. It is not necessarily to be 0. Can you imagine you drive a car, air is coming to the rooftop. It will touch the rooftop, then it will have the velocity of the car. It is not stopped, right? It is moving together with the car. Just like you within the car with your friend. Your friend looking at you, he's there, not moving. But Pak Guard, who is stopping you there, seeing you and your friends is moving together with the car. Right? So that's the concept of relativity. Okay, now Einstein is coming. That's the relativity theory. Okay, so but we will not talk about that. We just say about this no slip condition, basically meaning that if a moving fluid make a contact with the surface, it will have the velocity of the surface. It not necessarily to be 0. Okay, because why I emphasize that? Because in the flow scenario number 2, you will have the top plate or bottom plate moving. Any question about this thing? Now the problem is, can you use our newly derived Navier Stokes to represent this flow? How to solve it? This is the procedure. You need to sketch diagram, label all the axes, okay? It's common, right? From static, you have been trained how to do this. In fluid mechanics 1, in finite volume analysis, you need to draw the control volume, control surface, all the forces working on it, right? And then from that, you derive the equation. Okay, the same goes for that. Sketch diagram, label all the axes, and then boundary condition and diagram. Then the next one is list all assumption and condition. Because as I said to you, Navier Stokes is highly complex. It cannot be solved exactly at the moment without any assumption taken. Okay, if you do not take any assumption, it's very tough to solve it. Maybe one of you can solve it later on. But at the moment, there is no human can solve it. Analytically, right? Numerically, we can solve. Okay, so this one is very important. Apply the continuity equation, you know, the conservation of mass. Then apply the momentum equation. Solve the resulting differential equation. Apply the boundary condition. Then do whatever evaluation that you want to do. Okay, I will show you how to do that. Now let's list our assumption. Okay, first sketch the complete diagram. This is your case, this is your problem. So I give this direction as X, those direction as Y, and the direction going out of the screen is Z. Okay, if you ask me, can I choose my own coordinate? I do not want X, Y, Z, I want A, B, C. Up to you. Can. Just be consistent. Okay, just be consistent. Okay, maybe because you love A, B, C so much, right? You feel thirsty when you have A, B, C, so you just want to put A, B, C. It's okay, no problem, you can do that. Doesn't matter for me, right? Just be consistent. The gravity is there, and no slip condition will give you like that. Okay, now the condition. If you read the problem, instead what do you have there? Steady, incompressible, no slip condition. What else? Gravity is only in the Y direction.
Yes.
Okay. And you may not realize it, but it will be very important later on in deriving your equation. What else? What's the other condition? It's regarding the plate. The plate is fixed. Yes. Perpendicular. Parallel. In. That is very important. Why infinite is very important, I will tell you later.